Before we begin, let's look at a common chemical reaction, like the effect of water on iron. After a few days, we notice that the iron has rusted. The rusting of iron is an electrochemical process that begins with the transfer of electrons from iron to oxygen. A redox reaction is a type of electrochemical reaction where oxidation and reduction occur simultaneously. Redox is the short form for reduction and oxidation. In the earlier days, scientists came up with the classical concept of redox reactions. According to it, oxidation is defined as addition of oxygen or an electronegative element to a substance, or removal of hydrogen or an electropositive element from a substance. Reduction is the opposite of oxidation. Hence, reduction was defined as removal of oxygen or an electronegative element from a substance, or addition of hydrogen or an electropositive element to a substance. Thus, according to the classical concept, redox reactions can be illustrated as shown here. Let's look at some examples of redox reactions. Let's look at an example. Consider the common salt sodium chloride. Did you know sodium chloride is formed as a result of a redox reaction between sodium and chlorine? Let's understand how. Sodium is oxidized due to the addition of an electronegative element, chlorine. Simultaneously, chlorine is reduced because of the addition of an electropositive element, sodium. This proves that in a redox reaction, oxidation and reduction occur simultaneously. Did you know combustion is also a redox reaction? Here's a combustion reaction of a hydrocarbon, methane. We know that oxygen is required for combustion. Methane reacts with oxygen to give carbon dioxide and water. In this reaction, carbon is oxidized due to removal of hydrogen, and simultaneously, oxygen is reduced due to addition of hydrogen. In the final example, we will see a redox reaction between copper oxide and copper sulfide. Copper oxide reacts with copper sulfide to give copper and sulfur dioxide. In this reaction, oxygen, an electronegative element, is removed from copper oxide, and copper, an electropositive element, is removed from copper sulfide. According to the classical definition of oxidation, here are some examples of oxidation reactions. In the first equation, adding oxygen to magnesium gives us magnesium oxide. In the second equation, chlorine, an electronegative element, is added to magnesium. The result of this reaction is magnesium chloride. In the third equation, hydrogen is removed from methane, which is oxidized as carbon dioxide. The resultant product is carbon dioxide and water. In the fourth equation, potassium ferrocyanide reacts with hydrogen peroxide. Oxidation occurs due to the removal of electropositive element potassium from potassium ferrocyanide. According to the classical definition of reduction, here are some examples of reduction reactions. In the first equation, mercuric oxide on heating gets reduced and forms mercury and oxygen. In the second equation, when ferric chloride reacts with hydrogen, electronegative element, chlorine will be removed and ferrous chloride will be formed. In the third equation, by adding hydrogen to ethene, we get ethane. In the fourth equation, the reaction of mercuric chloride with stannic chloride produces mercurous chloride and stannic chloride. In this reaction, mercury, an electropositive element, is added to mercuric chloride. The electronic concept conveniently explains the redox reactions in terms of transfer of electrons from one species to the other. Let us see how. While the classical concept defines oxidation in terms of addition or removal of elements, the electronic concept defines it as loss of electrons. In a chemical reaction, during the formation of products from the reactants, the loss of electrons results in the increase of positive charge or decrease of negative charge of the species. We know that reduction is the opposite of oxidation. The classical concept defines that too in terms of addition or removal of elements. The electronic concept defines it as gain of electrons. The gain of electrons results in the decrease of positive charge or increase of negative charge of the species as we proceed from reactants to the products in a chemical reaction. Thus, according to electronic concept, a reaction in which loss of electrons, that is, oxidation and gain of electrons, that is, reduction, takes place simultaneously, is called redox reaction. The definition of oxidation and reduction can be easily remembered by the mnemonic OIL-REG, which stands for oxidation is loss of electrons and reduction is gain of electrons. Let's take the example of the formation of sodium chloride from sodium and chlorine. In this reaction, sodium loses an electron and forms Na+ ion, while chlorine gains an electron and forms Cl- ion. Hence, according to electronic concept, sodium is said to be oxidized, whereas chlorine is said to be reduced. The part of the reaction that involves loss of electrons is called oxidation half reaction, while the part that involves gain of electrons is called reduction half reaction. The sum of the half reactions gives us the complete redox reaction. In a redox reaction, the substance that donates electrons to reduce the other substance is known as a reducing agent. On the other hand, the substance that accepts electrons to oxidize another substance is known as an oxidizing agent. In this process, the reducing agent gets oxidized and oxidizing agent gets reduced. Thus, in the reaction between sodium and chlorine to form sodium chloride, sodium acts as a reducing agent by donating the electrons, while chlorine acts as an oxidizing agent by accepting the electrons. We know that metals show the tendency to lose electrons. The more easily a metal loses electrons, the more active it is. Let's try to understand this through the following activity. We have placed a zinc rod in an aqueous solution of copper nitrate. Let's observe what happens. After a while, we notice a reddish coating which is due to the deposition of metallic copper appearing on the rod. We also notice that the intensity of the blue color of copper nitrate decreases and becomes colorless after some time. This is due to the disappearance of Cu+2 ions, which are responsible for the blue color of the solution. Let's look at the chemical equation to understand what happened. In the reaction, zinc lost electrons to form Zn2+ ions. Therefore, zinc was oxidized. Simultaneously, Cu+2 ion was reduced to metallic copper as it gained electrons from zinc. Thus, we can conclude that zinc releases electrons to copper. Now let's place a copper rod in zinc sulfate solution and see if we get the same result. After a while, we notice that no reaction has occurred. We can confirm the same by passing hydrogen sulfide gas through the solution. If copper ions were present, a black precipitate of cupric sulfide would have appeared. Thus, we can conclude that copper does not release electrons to zinc. Now, let's extend the electron transfer reaction to copper metal and silver nitrate solution in water. Let's place a copper rod in an aqueous solution of silver nitrate and leave it undisturbed for some time. After a while, we notice that the solution has turned blue due to the release of copper ions from the copper rod into the solution. We also notice the deposition of metallic silver on the copper rod. In this reaction, copper is oxidized to Cu2+ ion and silver ion is reduced to metallic silver. This shows that copper releases electrons to silver. From the above experiments, we can conclude that among the three elements, zinc, copper and silver, zinc has the greater tendency to release electrons than copper and silver. This suggests that metals differ in their tendency to release electrons. Depending on the tendency of the metals to release electrons, metals are arranged in the form of a series. The series obtained when the metals are arranged in the decreasing order of their ability to donate electrons is known as metal activity series or electrochemical series. Thus, the knowledge of competition between the metals to release the electrons helps us to construct galvanic cells in which the chemical energy is converted into electrical energy. We learned that in redox reactions, transfer of electrons takes place. For example, if you look at the ionic reaction between sodium and chlorine, it is clear that sodium loses an electron and chlorine gains an electron to form sodium chloride. But how does one determine an electron transfer in the formation of a covalent compound like water? In the formation of water from its elements, we can assume that hydrogen and oxygen atoms are undergoing a change from neutral state to positive and negative state respectively. This we can predict is due to the transfer of an electron from hydrogen to oxygen. unlike ionic bonds, a complete electron transfer does not occur in covalent bonds. Instead, there is a partial transfer of electronic charge. This is known as an electron shift. In order to track the electron shifts occurring in covalent compounds, scientists came up with the concept of oxidation number. The oxidation number method always assumes that there is a complete transfer of electrons from a less electronegative atom to a more electronegative atom. For example, in the formation of water molecule, it is assumed that there is electron transfer from hydrogen atom to oxygen atom, and hence hydrogen gets oxidized and oxygen gets reduced. Note that the electrons in a covalent bond don't really get transferred. It is only a hypothetical assumption made for the purpose of understanding redox equations. Oxidation number is defined as the charge or the apparent charge that an atom in a compound or ion would have. If all the electrons in its bonds belonged entirely to the more electronegative atom. Oxidation number is also referred to as oxidation state. We will be using the term oxidation number throughout this module. To determine the oxidation number of an element in a compound or an ion, certain rules have been formulated. Let's look at these rules. The first rule is that the oxidation number of atoms of elements in their elementary states and allotropic forms is 0. For example, each atom in H2, O2, Cl2, O3, P4, S8, Na, Mg, Al has oxidation number 0. The second rule is that in neutral compounds, the sum of oxidation number of all atoms is 0. For example, in H2O, the sum of oxidation numbers of hydrogen and oxygen atoms is 0. The third rule is that in case of the ions that are composed only of one atom, the oxidation number is same as the charge on the ion. For example, the oxidation number of sodium ion is +1, magnesium ion is +2, ferric ion is +3, chloride ion is -1 and oxide ion is -2. However, in complex and polyatomic ions, the algebraic sum of the oxidation numbers of all atoms in the ion is equal to the charge on the ion. For example, in the carbonate ion, the algebraic sum of the oxidation numbers of the 3 oxygen atoms and 1 carbon atom is -2. The oxidation number of carbon is 4 and oxidation number of oxygen is -2. So 4 plus 3 multiplied by -2, which is 4 minus 6, is equal to -2. The fourth rule says that in their compounds, all alkali metals have oxidation number of +1 and all alkaline earth metals have oxidation number of +2. According to the fifth rule, the oxidation number of oxygen is -2 in most of its compounds, except in 2 cases. The first is the case of peroxides and superoxides. In peroxides like hydrogen peroxide and barium peroxide, each oxygen atom is assigned an oxidation number of -1. And in superoxides like potassium superoxide and rubidium superoxide, each oxygen atom is assigned an oxidation number of -12. Another exception is when oxygen combines with fluorine. For example, the oxidation number of oxygen in oxygen difluoride is +2, and in dioxygen difluoride it is +1. This is because fluorine is the most electronegative element and has an oxidation number of -1. The sixth rule says that hydrogen has +1 oxidation number when it combines with nonmetals. This is because all nonmetals are more electronegative than hydrogen. But hydrogen is more electronegative than metals. Hence, in metal hydrides, where hydrogen combines with metals such as lithium, potassium, and magnesium, its oxidation number is -1. According to the seventh rule, fluorine has an oxidation number of -1 in all its compounds. Other halogens such as chlorine, bromine, and iodine also have oxidation number of -1 when they occur as halide ions in their compounds. But when they combine with oxygen to form oxo acids and oxoanions, they have positive oxidation numbers. The atoms of transition or d block elements exhibit several oxidation numbers. The table shown here depicts the variable oxidation states exhibited by the transition elements. The highest oxidation number of a representative element is the group number for the first two groups and the group number -10 for the remaining groups. This shows that the highest value of oxidation number exhibited by an atom of an element increases across the period in the periodic table. For example, the valence shell configuration of the 13th group elements is Ns2, Np1. They have 3 electrons in their valence shell that they can lose to obtain their octet configuration. Hence, the group 13 elements exhibit highest oxidation state of +3 in their compounds. The same trend applies to all elements from the 13th to the 17th group. In other words, the highest positive oxidation number for p block elements is equal to the group number -10. Now, let's apply what we have learnt and determine the oxidation number of sulfur in hydrogen sulfide. According to Rule 6, the oxidation number of hydrogen is +1 when combined with nonmetals. In this case, sulfur. Let us assume the oxidation number of sulfur to be X. We will write the oxidation numbers of the atoms above the chemical symbols. If we calculate the sum of the oxidation numbers of the atoms, we get the result as shown here. According to Rule 2, the sum of oxidation numbers of atoms in a neutral compound is 0. Therefore, we will add 0 to the equation. As per the equation, the oxidation number of sulfur in hydrogen sulfide is -2. We learnt that certain elements exhibit more than one oxidation number. For example, the oxidation number of copper in Cu2O is +1, while the oxidation number in CuO is +2. How is the oxidation number of such elements indicated in a compound? Alfred Stock, a German chemist, introduced a nomenclature system to indicate oxidation numbers for metals that exhibit more than one oxidation number. The nomenclature, known as Stock notation, indicates the oxidation number by placing a Roman numeral within parentheses after the symbol or name of the metal. Thus, the oxidation numbers for copper in both compounds can be indicated as shown. Based on the nature of the reaction, redox reactions are divided into 4 types. These are combination reactions, decomposition reactions, displacement reactions, and disproportionation reactions. Let's look at each type of the reactions. As the name implies, a combination reaction is a chemical reaction in which 2 or more substances combine to form a single new substance. A combination reaction can be represented as A plus B gives rise to C. For a combination reaction to be a redox reaction, either A or B or both should be in elemental state. We know from the oxidation number rules that atoms of elements in elemental states have an oxidation number of 0. Thus, when substances with 0 oxidation number combine, one substance will be oxidized and the other will be reduced. Let's look at some examples of redox combination reactions. Carbon and oxygen in elemental states combine to give carbon dioxide gas. The oxidation number of carbon and oxygen is 0. When carbon dioxide gas is formed, the oxidation number of carbon becomes +4 and oxidation number of oxygen becomes -2. Here, carbon undergoes oxidation. As its oxidation number increases from 0 to +4. Simultaneously, oxygen undergoes reduction, as its oxidation number decreases from 0 to -2. Magnesium reacts with nitrogen to give magnesium nitride. In this reaction, the oxidation number of magnesium changes to +2 from 0, as it is oxidized. Simultaneously, the oxidation number of nitrogen changes from 0 to -3, as it is reduced. Now let's look at decomposition reactions. Decomposition means breakdown. Thus, a decomposition reaction is a chemical reaction in which a compound breaks down into 2 or more substances. It is the opposite of combination reaction and can be represented as shown here. For a decomposition reaction to be a redox reaction, it is essential that at least one of the product of the decomposition reaction is in the elemental state. One of the most common examples of a decomposition reaction is the breakdown of water into hydrogen and oxygen. The oxidation number of hydrogen decreases from +1 to 0 as it gets reduced, while oxidation number of oxygen increases from -2 to 0 as it gets oxidized. Note that as the products, hydrogen and oxygen of this reaction are in the elemental state, it is a redox decomposition reaction. In this example, potassium chlorate decomposes to form potassium chloride and oxygen. One of the two products, oxygen, is present in elemental state. Hence, this reaction is a redox decomposition reaction. The oxidation number of chlorine decreases from +5 to -1 as it gets reduced, while oxidation number of oxygen increases from -2 to 0 as it gets oxidized. Note that there is no change in the oxidation state of potassium. Now, consider the decomposition of calcium carbonate. The products we get are calcium oxide and carbon dioxide. As none of the products are in the elemental state, and as there is no change in oxidation state of any element, this reaction is not a redox decomposition reaction. The third category of reactions is the displacement reactions. In a displacement reaction, the atom or ion in a compound is replaced by the atom or ion of some other element. The reaction can be expressed as X plus YZ converts to XZ plus Y. In this reaction, from the compound YZ, Y has been displaced by X. Displacement reactions are of two types: metal displacement reactions and non-metal displacement reactions. In a metal displacement reaction, the metal in a compound is displaced by some other metal in the elemental state. For example, in this reaction, copper sulfate reacts with zinc to form copper and zinc sulfate. This is a displacement reaction because copper has been displaced by zinc. The oxidation number of copper has decreased from +2 to 0. Hence, copper is reduced. Simultaneously, the oxidation number of zinc is increased from 0 to +2. Hence, zinc is oxidized. Thus, the reaction as a whole is a redox displacement reaction. In this reaction, titanium tetrachloride and magnesium react to form titanium and magnesium chloride. As you can see, magnesium has replaced titanium to form magnesium chloride. The oxidation number of titanium has changed from +4 to 0, and magnesium from 0 to +2 oxidation state. Thus, this reaction is also a redox displacement reaction. Similarly, in this reaction between chromium trioxide and aluminium, aluminium replaces chromium to form aluminium oxide. In each of the metal displacement reaction, a metal displaces another metal, and the reducing metals like zinc, magnesium and aluminium are better reducing agents than copper, titanium and chromium. That is, the metal being reduced. The second type of displacement reaction is the non-metal displacement reaction. In a non-metal displacement reaction, a metal or a non-metal displaces another non-metal in a compound. In most non-metal reactions, the non-metal displaced is hydrogen. However, some reactions involve displacement of oxygen or halogens. Let's look at examples of metals displacing nonmetals. All alkali metals and certain alkaline earth metals displace hydrogen from cold water. For example, sodium, an alkali metal, displaces hydrogen from cold water to give dihydrogen gas. Similarly, calcium, an alkaline earth metal, reacts with cold water to displace hydrogen. Less reactive metals like magnesium and iron react with steam to produce dihydrogen gas. For example, magnesium reacts with steam to produce magnesium hydroxide and hydrogen gas. Similarly, iron reacts with steam to form iron 3 oxide and hydrogen gas. Many metals, including those that do not react with cold water, can displace hydrogen from acids to liberate dihydrogen gas and the respective salt. For example, zinc reacts with hydrochloric acid and displaces hydrogen to form zinc chloride and dihydrogen gas. Similarly, magnesium and iron react with hydrochloric acid and displace hydrogen from hydrochloric acid to liberate dihydrogen gas along with the formation of magnesium chloride and iron chloride respectively. Very less reactive metals like silver and gold do not react with hydrochloric acid and hence cannot displace hydrogen. We learnt about the activity series of metals and saw that zinc releases electrons to copper and copper releases electrons to silver. Similarly, halogens also have an activity series. The halogens in 17th group include fluorine, chlorine, bromine, and iodine. These halogens have a tendency to accept electrons as they need an electron to complete their octet. This tendency causes them to be reduced. Hence, they are good oxidizing agents. The oxidizing power of these halogens reduces as we move down group 17, with fluorine being the highest and iodine being the lowest. Fluorine is highly reactive and can displace chloride, bromide, and iodide ions in a solution. Due to its high reactivity, it can also displace oxygen from water. Therefore, displacement reactions of chloride, bromide, and iodide ions with fluorine are not carried out in aqueous solutions. Let's look at some more halogen displacement reactions. In these reactions, chlorine displaces bromide and iodide ions from the aqueous solutions of their salts. These reactions are used to identify bromide and iodide ions as the bromine and iodine produced have characteristic colors. This identification is called as layer test. Similarly, bromine can displace iodide ions in an aqueous solution. Halogen displacement reactions are used in industrial applications to produce chemicals, such as hydrofluoric acid, which is used to etch glass. Did you know that while there are a number of oxidizing agents that can oxidize chloride, bromide, and iodide ions, no oxidizing agent is available to oxidize fluoride ions. This is because fluorine is the strongest oxidizing agent. The only way to prepare fluorine is to oxidize fluoride ion electrolytically. Finally, let's look at the last type of reaction: disproportionation reaction. A disproportionation reaction is a reaction in which the same element is oxidized as well as reduced. For such reactions to occur, one of the reacting elements should exist in at least 3 oxidation states. For example, the decomposition of hydrogen peroxide is a disproportionation reaction. Here, oxygen has a -1 oxidation number in hydrogen peroxide. It gains electrons and increases to 0 in O2 and decreases to -2 in water. Here is a disproportionation reaction that illustrates the preparation of household bleaching agents. In this reaction, hypochlorite ion, which shows bleaching action, is formed by dissolving chlorine in alkali. Chlorine, having an oxidation state of 0, is being reduced to -1 in chloride ion and also being oxidized to +1 in hypochlorite ion. Note that, like chlorine and bromine, iodine also undergoes disproportionation. However, fluorine with alkali does not show a tendency to undergo a disproportionation reaction. This is because fluorine is the most electronegative element and hence cannot exhibit any positive oxidation state. There are 2 methods to balance redox equations: the oxidation number method and the half reaction method, also known as the ion-electron method. The oxidation number method is based on the change in the oxidation number of the reducing and oxidizing agent. The half reaction method is based on splitting the redox reaction into 2 halves, the oxidation half and the reduction half. Let's discuss the various steps to balance the redox equation using the oxidation number method with the help of an example. In this reaction, permanganate ion reacts with bromide ion in basic medium to give manganese dioxide and bromate ion. In the first step, write down the correct formula of all the reactants and products in the reaction. The second step involves assigning the oxidation numbers to all the elements in the reaction and also identifying the atoms which undergo change in the oxidation number. We know that in polyatomic ions, the sum of the oxidation numbers of all atoms in the ion is equal to the charge on the ion. Thus, the oxidation number of manganese in permanganate ion may be calculated as follows. Let the oxidation number of manganese be X. We know that the oxidation number of oxygen is -2. Hence, X plus 4 multiplied by -2 equals -1. Therefore, X equals to +7. Thus, the oxidation number of manganese is +7. We also know that the oxidation number of a monoatomic ion is same as the charge on the ion. So, in the case of bromide ion, the oxidation number will be -1. Now let us focus on the products. First, we'll calculate the oxidation number of manganese in manganese dioxide. We put the oxidation number of manganese as X. X plus 2 multiplied by -2 is 0. So, X plus -4 is 0. Hence, X equals +4. Next, we'll calculate the oxidation number of bromine in bromate ion. Let us consider the oxidation number of bromine in bromate ion as X. X plus 3 multiplied by -2 is equal to -1. Thus, X is equal to +5. Now, observe the change in the oxidation number of the elements. The oxidation number of manganese changes from +7 to +4, and the oxidation number of bromine changes from -1 to +5. Note that oxygen does not undergo any change in oxidation number. In the third step, calculate the total increase or decrease in oxidation number per atom and for the entire molecule or ion in which it occurs. If the increase or decrease in oxidation number is not the same, then equalize them by multiplying with suitable coefficients. In this case, the decrease in oxidation number of manganese is 3. While the increase in oxidation number of bromine is 6. Hence, to make the decrease equal to the increase, we multiply the decrease in oxidation number, that is, 3 with 2. Which means that we introduce a coefficient of 2 with manganese on the left and the right-hand side of the equation. Now, let's come to the fourth step. Identify the involvement of ions and balance the ionic charges. If the reaction takes place in water, then add H plus or OH minus ions on the appropriate side, so that the total ionic charge of reactants and products is equal. If the reaction takes place in an acidic solution, then add H plus ions. If the reaction takes place in a basic solution, then add OH minus ions. As the reaction occurs in the basic medium and the ionic charges are not equal on both sides, we need to add 2 OH minus ions to the right side of the equation, so that the ionic charges are balanced. Finally, balance the number of hydrogen atoms. This can be done by adding H2O molecules to the reactants or products as applicable. In this case, we have 2 hydrogen atoms on the right-hand side and no hydrogen atoms on the left-hand side. Hence, add 1 water molecule on the left-hand side to balance the hydrogen atoms. Now, also check the oxygen atoms. If the numbers of oxygen atoms on the reactant and product side are same, then we can say that the equation represents a balanced redox reaction. In this case, if we count the number of oxygen atoms on either side of the reaction, we can see that there are 9 oxygen atoms present on either side. And thus, the equation represents a balanced redox reaction. The half reaction method is based on the principle that electrons lost during the oxidation half reaction are equal to the electrons gained during the reduction half reaction. Let's look at an example. In this reaction, dichromate ions in aqueous acidic medium reacts with ferrous ions to give ferric and chromium 3 ions. Let's look at the steps involved. First, write the skeletal equation for the reaction in the ionic form. Then identify the species which have been oxidized and reduced, and split the reaction into 2 half reactions. This is step 2. In this case, the oxidation number of chromium decreases from +6 to +3. Thus, dichromate ion is reduced. Simultaneously, the oxidation number of iron increases from +2 to +3. Thus, iron is oxidized. Thus, the 2 half reactions can be written to show the oxidation half reaction and the reduction half reaction. In the third step, balance all atoms except oxygen and hydrogen. In this example, the oxidation half reaction is already balanced since the numbers of iron atoms are equal on either side of the equation. In the reduction half reaction, there are 2 chromium atoms on the left-hand side and only 1 on the right-hand side. So, we'll multiply Cr3 plus by 2 to get 2 chromium atoms on the right side too. Now in the fourth step, balance the H and O atoms. If the reaction takes place in an acidic medium, add H2O to balance O atoms and H plus to balance H atoms. If the reaction takes place in a basic medium, add H2O to balance oxygen atoms and OH minus ions to balance hydrogen atoms. In this case, in the oxidation half, there are neither oxygen nor hydrogen atoms. But in the reduction half, you can see that there are 7 oxygen atoms on the left-hand side, but no oxygen atom on the right-hand side. As the reaction occurs in acidic medium, to balance 7 oxygen atoms on left-hand side, we add 7 H2O molecules on the right-hand side. Now, after the addition of 7 water molecules, there are 14 hydrogen atoms on the right-hand side, but no hydrogen atom on the left-hand side. Hence, to balance the hydrogen atoms, we add 14 H plus ions on the left-hand side. In the fifth step, balance the charge by adding electrons to one side of the each half reaction. If required, make the number of electrons equal in the 2 half reactions by multiplying one or both half reactions by appropriate coefficients. The charge of iron on the right-hand side is +3, while on the left-hand side it is +2. Therefore, to balance the charge, we will add 1 electron to the right-hand side. In the reduction half reaction, there are net 12 positive charges on the left-hand side and only 6 positive charges on the right-hand side. Hence, to balance the charge, we add 6 electrons on the left-hand side. To balance the electrons lost in the oxidation half and gained in the reduction half, we multiply the oxidation half by 6. In the sixth step, add the 2 half equations to obtain the overall reaction and cancel the electrons on each side. Thus, we obtain the net ionic equation as shown. Finally, verify the equation by ascertaining that the same type and same number of atoms and charges exist on both sides of the equation. Since the charges on both sides are equal, this is a balanced redox equation. Titrations that involve oxidation, reduction reactions are known as redox titrations. Redox titrations are used to determine the strength of a reductant or oxidant by using a redox sensitive indicator. Redox titrations can be performed using oxidizing agents such as potassium permanganate, potassium dichromate, and iodine. Let's look at each of them. Potassium permanganate is a dark purple-colored liquid and a versatile and strong oxidizing agent used in the estimation of many reducing agents such as iron +2 ions, oxalate ions, etc. Indicators are not used in these titrations as potassium permanganate acts as a self-indicator. During the titration between potassium permanganate and a reducing agent, the pink color of potassium permanganate is discharged till the reductant is completely oxidized. A further addition of a single drop of potassium permanganate gives a tinge of pink color to the solution. This indicates the end point of the titration. In the redox titration reactions, where the oxidizing agent doesn't act as self-indicator, indicators such as diphenylamine or N-phenylanthranilic acid are used. These indicators are oxidized immediately after the last bit of the reactant is consumed, producing dramatic color change. For example, in the estimation of iron using potassium dichromate, diphenylamine is used as an indicator to detect the end point. In this reaction, potassium dichromate oxidizes diphenylamine just after the equivalence point to produce violet blue color, thus indicating the end of the titration. The other class of titrations, which include iodine as the oxidizing agent, are iodimetric titrations and iodometric titrations. The titrations in which iodine is directly titrated against a reducing agent are called iodimetric titrations. For example, in the estimation of hypo or sodium thiosulfate, iodine directly reacts with sodium thiosulfate in the presence of starch as an indicator and produces an intense blue color. Iodometric titrations, on the other hand, involve the addition of an oxidizing agent to excess iodide ions to produce iodine, which is then titrated with standard thiosulfate solution. For example, in the estimation of Cu+2 ions, iodine is liberated by oxidizing iodide ions from potassium iodide. An intense blue color develops when starch solution is added to the liberated iodine. This solution is titrated against sodium thiosulfate solution. The color disappears as soon as the iodine is consumed by the thiosulfate ions. Thus, the end point is detected easily by noting the color change. It must be remembered that iodine, being nonpolar, is very slightly soluble in water. However, it dissolves in water in the presence of potassium iodide due to the formation of I3- ions. Let's revisit the redox reaction that we've seen. Here, we place a zinc rod in copper nitrate solution. After a while, the color of the solution becomes pale blue, and finally, it becomes colorless. The zinc rod, on the other hand, gets coated with reddish metallic copper. In this reaction, zinc is oxidized to zinc ions and copper 2 plus ions are reduced to form copper. This reaction took place in an open vessel, and the chemical energy from the reaction was released as heat. Think about it. Is it possible to convert the chemical energy into electrical energy? Yes, it is. Let's see how. We place the zinc rod in 1 molar zinc sulfate solution. Then, we place the copper rod in 1 molar copper sulfate solution. In each beaker, the reaction takes place at the interface between the metal and its salt solution, and both the oxidized and reduced forms of the same species are present. This is also known as a redox couple. A redox couple is defined as a combination of the oxidized and reduced forms of the same substance taking part in a redox reaction. Now, we connect the two solutions by using a salt bridge. A salt bridge is a U-tube filled with potassium chloride or ammonium nitrate, usually solidified by boiling with agar and later cooling to a jelly-like substance. It is an inert electrolyte and is a substance whose ions neither take part in a redox reaction nor do react with the solutions in the two beakers. Next, we connect the two ends of a voltmeter to zinc and copper electrodes by means of wires. When the switch is in the off position, no reaction takes place and current does not flow. As soon as the switch is in the on position, current flows and the reading in the voltmeter changes, indicating that current is passing through it. The current is caused due to the chemical reaction taking place between the two beakers. Since zinc is a more active metal than copper, it loses electrons and gets oxidized. The equation for this reaction can be expressed as zinc atom loses 2 electrons to form zinc ions. The electrons move through the voltmeter wire and reach the copper rod. When the electrons lost by zinc reach the copper rod, they combine with the copper 2 plus ions to form neutral copper atoms, which get deposited on the copper rod. The equation for this reaction can be expressed as copper 2 plus ions gain 2 electrons and form copper metal. As the reaction continues, the excess zinc ions accumulate around the zinc rod in the zinc solution. Due to this, any further oxidation of zinc stops as the repulsion among Zn2 plus ions increases. Similarly, copper 2 plus ions reduce to copper atoms and deposit on the copper rod. This loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions in the solution. This prevents the further reduction of copper ions. As a result, the overall reaction stops and also the current in the setup stops. To avoid such a situation, the salt bridge plays an active role. The positive potassium ions move from the salt bridge into the copper solution, thereby neutralizing the negative charge. On the other hand, the negative chloride ions move from the salt bridge into the zinc solution and neutralize the positive charge. Thus, reaction goes on continuously till the solutions get exhausted. The reaction stops when either the zinc rod or the copper ions are depleted. The overall equation for the reaction is copper 2 ions react with zinc metal to form zinc 2 plus ions and copper. Note that Zn loses electrons and undergoes oxidation, and hence the beaker in which zinc rod is immersed in zinc sulfate solution is called oxidation half cell. The electrode at which oxidation takes place is called anode. On the other hand, the beaker in which copper rod is dipped in copper sulfate solution, reduction of copper ions is taking place and is referred to as reduction half cell. The electrode at which reduction takes place is called cathode. During the cell notation, a slash is used to separate the oxidized form and the reduced form in a couple. The overall cell is represented by writing oxidation half cell on the left-hand side and reduction half cell on the right-hand side, both separated by two vertical lines. Electrons produced at anode due to oxidation of zinc travel through the external circuit to cathode, where they reduce copper ions. Note that the current flow is in the opposite direction to the electron flow. In this experiment, the two redox couples are zinc and zinc 2 plus ions and copper 2 plus ions and copper. The apparatus set up for this experiment is known as the galvanic cell. The galvanic cell was invented by an Italian anatomist, Luigi Galvani. Note that there are many factors that determine the amount of electric current produced by a galvanic cell. The most important factor is the tendency of a metal to lose electrons. Between the two electrodes, one has a tendency to lose electrons, while the other has a tendency to gain electrons. The potential of any electrode, commonly known as electrode potential, is the potential difference between it and the electrolyte surrounding the electrode. The electrode potential of an electrode depends on the nature of the metal, concentration of the ions, and the temperature of an electrolyte. If the concentration of each species taking part in the electrode reaction is taken as unity and temperature is taken as 298 Kelvin, then the potential of each electrode is known as the standard electrode potential and is represented as E0. By convention, the standard electrode potential of hydrogen electrode is taken as 0. Chemists have created a table that lists the tendency of various substances to lose electrons in a galvanic cell. Note that the values of standard electrode potentials are relative to the standard hydrogen electrode. a metal with a higher standard reduction potential can be easily reduced, and hence is a better oxidizing agent. For example, fluorine has a standard electrode potential of plus 2.87 volts, while lithium has a standard potential of minus 3.05 volts. Thus, fluorine reduces easily and is the strongest oxidizing agent. On the other hand, lithium undergoes oxidation as is the strongest reducing agent.